All right. So we finally know how to talk about the category of schemes, thanks to Ty's work the last time we met, because we now have the notion of morphisms. We talked about the objects for the longest time. We've been talking about schemes the entire existence of the seminar in some way, shape, or form. But, well, we probably haven't seen enough about morphisms yet, so that's what we're going to do today. First of all, we need some examples, because we don't have any yet. So we'll see a couple of them, and also some facts about the category of schemes. For instance, what the final object of this category is, and some various related constructions you can do, different categories, category of S schemes, and talk about points of a scheme that take values in other schemes, and strange things like this. But before any of that, I just want to quickly go back over some of the highlights from what Ty talked about. Just give us a recap of what morphisms are before actually talking about them. So, given schemes, x and y, so what's a morphism going to be between these? Oh, we need to preserve basically all the structure we care about with schemes. So the compact way of saying this is just a morphism in the category of locally ringed spaces, but we have to unpack what that means too. So the first feature is a continuous map of the underlying topological spaces. Which by abusive notation we call pi as well. Okay, so that's fine. And this was sort of motivated by what we do in other geometric categories, like category of differentiable manifolds or some such thing. And Ty gave a very excellent motivation for why the other two conditions I'm about to state pop up, because these are things that happen automatically when you try and do this kind of construction in one of these differentiable manifold categories or such things. It's as soon as you have, well, maybe not just continuous, but like smooth or some nice map, you can talk about functions on your manifold and you can pull them back from the target to the original one. And that's just forced on you by the fact that you have a nice map from one to the other. With schemes, alas, we don't have that. So we have to just say how to pull functions back, because we still want to be able to do this. So this is the second part of the morphism. So we get a morphism on the sheaves, which we think of as being functions. And Vakil likes to use pi sharp for some reason, so I'll do that today. This goes from functions on y back to basically functions on x, but because of the technical reason that we can only talk about morphisms of sheaves in the same base, we have to just push forward the sheaf to y, but whatever. We just renamed our open sets, basically. Okay, so we got a continuous map, and we say how we pull functions back. But there's another feature we want, which is also automatic in these nicer categories, which is if you want to talk about functions vanishing at a point, and you pull back a function from one to the other, then any preimage at this point, the pullback should vanish there. And, well, again, with sheaves, we'll have to build this into our definition. So as soon as we write down one of these morphisms of sheaves, we get an induced one on stalks. So the induced morphism on stalks let's say this. So we pick our favorite point Q living in Y, and we can go from local ring, or the stalk at Q, over to a stalk at P, where P is any preimage of Q. So Q will be pi of P. This has to be a homomorphism of local rings. So that just means if I've got the maximal ideal of this one, and I take the image, it's got to land inside the maximal ideal for P. So if I pull back anything that vanishes at Q, it's got to vanish at P. Okay, so having done all this, we've sort of captured all the geometric intuition and information that we really want to have happen. But so far, this is all just a bunch of abstract stuff. So on the level of affine schemes, we said a few words about what exactly this looks like. So this I also want to recap. So for affine schemes, at the end of the day, you end up with an equivalence of categories between affine schemes and rings. So morphisms between affine schemes are completely determined by homomorphisms between underlying rings. So we can see this given a ring homomorphism. Say phi from B to A. So we get an induced map on schemes. Running the other way. And long, long ago, we said at least what this does in the level of topological spaces. And Ty also mentioned this again last time. But so for points, well, you want to take the image of a prime ideal, you just take the pre-image of this prime ideal under the ring homomorphism, and we're good. Because the pre-image of prime ideals are, again, prime ideals. What makes this thing continuous, though, is it's happily arranged so that the pre-image of a distinguished open set is again a distinguished open set. And this is enough for the continuity bit. So if you want the pre-image of some df living in my target spec B, you can just run through these definitions and it works out to be d of phi of f. So it's continuous. Okay, the new ingredient from last time was just what we're going to do on the sheaves. And like many constructions, we only really worry about the distinguished open sets. And since this is a base for the topology, it determines the morphism on all the open sets uniquely in sort of the standard ways. So if you want to start with, you want to go from sections over some df inside of spec B. And what you're going to end up with is, well, something for spec A over the pre-image of this open set, which we said was d of phi of f. Okay, but we know we can basically identify these with B localized at f, this one with A localized at phi of f. Nope, we're good, okay. And then we have a built-in ring homomorphism from B to A. And these are just some fractions of things from B and some fractions of things from A. So if you've got, basically, you want to apply this to some element B over power of f. Well, here we go. All is well. There is some well-definedness that must be checked. If you switch out df with dh or something that gives you the same open set, you have to check that this gives you the same map. But this can be done. Okay, so this is the map we get on the affine schemes whenever we have a ring homomorphism. And Vakil manages to prove, he actually gives you the whole proof. So if we're given a morphism of schemes from one affine scheme to another, well, it comes from one of these ring homomorphisms, and not just any old ring homomorphism, it's the one on global sections. So this 2 would be one of the things you can do with PySharp, just on the entire space. This gives us a ring homomorphism from here to here. But these are, of course, B and A, respectively. So there we have it. Okay. So thus, we get an equivalence of categories using functor spec. We just take a ring to its spec. We take a ring homomorphism to this lovely construction here. And I will say something about exactly why we get an equivalence, because maybe you've forgotten exactly what this means. So there are 2 aspects to this. There's fully faithful and essentially surjective. And I'll start with the latter. So spec being essentially surjective is just the claim that for every affine scheme, there's something in the image of the functor isomorphic to it. But by definition of affine scheme, it's exactly the things isomorphic to spec of a ring, so here we go. The fully faithful part is if we've got a ring B and a ring A, that we should get a bijection between homomorphisms from B to A and morphisms from spec A to spec B. And that's just exactly this fact, that there's a one-to-one correspondence between ring homomorphisms and morphisms of schemes that gets recovered in this way. In particular, this is going to let us check that 2 morphisms between affine schemes are the same by avoiding a lot of work. All you have to do is check that the induced morphism on global sections is the same, and they have to be the same morphism. So we really only have to check equality of ring homomorphisms rather than equality of complicated scheme maps. So this trick will come up as we go on. Okay, so this was the quick 10-15 minute recall of your lovely talk last time. Anybody have any questions or complaints before we move on? Okay. So there's one thing I should say before we go too far. And that would be to give you an example. So this equivalence of categories tells us, at least for affine schemes, if I write down a ring homomorphism, I automatically get one of these morphisms. So pick your favorite. There's going to be 2 I'm going to isolate here because of their interest. So example 1 is consider complex conjugation. Say sigma from C to C. Okay, there's a ring homomorphism. Ergo, it induces a map on schemes from spec C back to spec C. So we get an induced map. I'll keep calling it pi. Spec C, spec C. Note, spec C has 1 point. but pi is not trivial. It is trivial on the level of topological spaces, but because we have this sheaf structure, it's definitely not the trivial map. In particular, the only relevant morphism between sections is the one between global sections, and it's got to be complex conjugation from C to C. It's not the identity map. So we get this weird behavior. Okay. The other one that will be of interest to us a little later is what you get when you consider quotient maps. And this leads to the somewhat complicated notion of closed subschemes. Okay, two quotient maps A to A mod I for any ideal we like. So this gives us a mapping of spec A mod I into spec A. Okay, but we mentioned long ago this identifies this map It identifies spec A mod I with a closed subset. The image of this set is a closed subset of spec A. Namely, V of I. Because the spec is just, as it is, the collection of prime ideals that contain I. And the induced map we're getting, at least on the level of points, is just to take pre-images under the quotient map. So you're just lifting the prime ideal from the quotient up to the original ring. This is exactly how the correspondence theorem works, there being a bijection between prime ideals containing I and prime ideals of A mod I. So this will lead, eventually, to the idea of a closed subscheme. In essence, the affine model that we want, what it looks like on affines when you're talking about closed subschemes, is going to be this kind of thing. And the reason it's complicated and Vakil defers it to later is because the image, I can choose two different ideals for which the image under this map is going to give me the same thing on a level of sets. It's just going to be different on the level of the sheaves. So you can think of it like I've got affine space here, so like k of x, and my ideal that I quotient by is either x or generated by x or generated by x squared. Well, the prime ideals containing x or x squared, it's the same. But at the same time, because I've quotiented by a different ideal, these maps are genuinely different on the level of sheaves. So the same set can get multiple structures as a closed subscheme, and this is why this is sort of a issue that's left for a little later. Okay. So these are the two affine types of affine examples I wanted to single out. Okay, everybody still okay? So the other thing I should talk about is gluing, because we glue everything else, so why not morphisms? So given schemes x and y, and some open cover of x, well, if I've got morphisms from these opens into y that appropriately agree on overlaps, I should, morally speaking, be able to glue them together to a morphism on everything. such that, and what have we got? Pi I restricted to this intersection is pi j. Also restricted to the intersection. Then there's a glue. Unique, in fact. Unique one of these that restricts to these maps on the UIs.
So over here, when you're talking about two morphisms being the same, these open covers aren't necessarily affine, right? They're just open covers?
Yeah, just your favorite open cover.
So can you just think of this, if you're going to check the two morphisms are the same, can you just say they're the same on the topological underlying space and at each stalk is the same map of local rings? Is that enough to say they're the same scheme map?
Yes.
Yeah.
Yeah. Two morphisms will agree exactly when the induced morphisms on all stalks agree as well.
Right, okay.
But my preferred way of doing this in a lot of cases is to cover this intersection with affines, prove that the further restriction to all the affines agree by giving the same morphism, and then...
Right, and then just check the ring homomorphisms.
Yeah.
Agree. Okay.
Yeah. But yeah, there's probably a myriad number of ways to check agreement on overlaps. Okay, but I don't want to actually prove this whole blasted thing. I just want to maybe say a few words about how one does this. So on the level of sets and topological spaces, it's basically forced on you. Because you want to define this at some point in X, well, I just pick one of these open sets in which it lives, I apply the applicable map to it, and the fact that they agree on overlaps tells me it's a well-defined choice, regardless of which open set I started with. Okay, but with the sheaves, well, you would expect that we'd try and use the gluability axiom in some way. If we're gluing morphisms, we want to be able to glue sections as well. So the only thing that might hang you up is to actually figure out what exactly this means when you're trying to write down morphisms of sheaves. What is a restriction if we're talking about this? So for on sheaves, well, this is actually true for the morphisms too. Saying this restriction is the same as this one is the same as saying if I take an inclusion of ui intersect uj into ui and then follow it up with pi I, it's the same as this other inclusion. So I'll call it, hopefully you forgive me, iota I and iota j. Where iota I into here is inclusion, iota j similar. Okay. So once you've wrote this down, well then you can say on the level of the sheaves, I can just take sharps of both these things. And because maps on sheaves always go in the opposite direction to maps on the originals, this is going to be reversing the order. So iota I sharp composed with pi I sharp equals iota j sharp composed with pi j sharp.
So here, iota I and pi I are continuous maps.
Morphisms of schemes. Full-on morphisms of schemes.
Sorry, and what's sharp? Can you remind me what sharp is?
The induced morphism on the sheaves that we get from.
Oh, sorry,
Yeah.
of course, okay.
It's just part of this data. Okay. But we also have to make sense of what these iota I and iota j sharps are. When you include some open subset into another open subset, what's the natural way to get a map going the other way on sections. Restriction, exactly. So, unwrapping all of this, this amounts to the claim that for every open set of Y, for all opens V inside of Y, and elements that are sections over V, when I hit it with these two maps, I should get the same thing. So on this side, I get the induced map on the open set V, well, really, on S, which I must then restrict to the intersection. So I'm going to write an intersection of open sets I've not defined yet and then tell you what they are. Wi intersect Wj, where, okay, Wi is the pre-image of V under pi I and V under pi j. Okay. Everybody still on board? Because these pi i's had to map up to relabeling of open sets. I had to take something defined here and map it to something on OX defined over the pre-image of V. And then they had to agree on this intersection, so then we drop to the intersection and they have to agree on the overlaps. So as soon as you've wrote this down, then the natural thing you want to try and do to define this map globally works. I've got the same old section on this open set, and I want to map it over to, well, some section on OX over the pre-image of V. Well, I can apply each of these maps to S. That's certainly well defined. And this gives me sections over these various pre-images of V. But the total pre-image of V under my glued topological map is the union of all of these things. So I've just given you sections on an open cover of my target set that restrict to be equal on the overlaps. Therefore, I can glue them and give you a global thing. And then you have to check that, well, it's compatible with restrictions, it's a homomorphism, da-da-da-da. But that bit's just technical messing around. Something you don't want to do in public in front of an audience. Okay, but this should be at least the key that unwraps the argument for you. Okay. And from now on, we can just say we can glue morphisms, and that's that, and we'll just use it. Okay. So where this first comes up is there's this key proposition, which I'm going to state first. And it has two interesting consequences. One of them is going to give us the final object in the category of schemes. The other one's going to give us an interesting auxiliary definition, a different category that we can define. And this will tell us that it's a nice definition, basically. Okay. So key proposition, which hopefully I have the time to sketch part of the proof of anyway. The claim is there is a natural bijection between morphisms from some scheme to an affine scheme and ring homomorphisms from A to global sections of the structure sheaf of X. So this is just generalizing something we already know to be true for affine schemes. If I take X equals spec B, it's a natural bijection between morphisms from spec B to spec A and ring homomorphisms from A to B, because global sections of spec B is B. And this is just stating that equivalence of categories that we already know to be the case. So this is just the natural extension of this. Okay. Proof later. Hopefully today. Otherwise, the next speaker will have to do this. But
can you just say something about what the bijection is?
sure. In one direction, so if I've got one of these morphisms, I just take global sections, I get an induced map that does this. If I want to go the other way, the inverse map is a little trickier. You have to break up X into affine opens, compose with restriction maps, you get morphisms you can glue, and then we get the morphism we want. So we'll spell that out if I have time. Okay, but a nice corollary of this that happens right away is that the final object in the category of schemes is, drum roll, some of you may know this already, spec Z. That's the one. So the proof, what does this even mean? There should be a unique morphism from any scheme to spec Z. That's what a final object is, what it means. So we want a unique map X to spec Z for any scheme X. But maps of this form are in bijection with ring homomorphisms from Z into global sections of X. These are in bijection with ring maps from Z to here. But the integers are the initial object in the category of rings. There is exactly one ring homomorphism from the integers into any ring that you please. Because I have to send 1 to 1, and that forces the generator of Z to go somewhere, and then you're stuck. You've defined the map everywhere. So only one of the latter. So only one of the former. So not the way I would have guessed you would prove this is the final object, but it certainly works. Okay. So the other thing I want to use this proposition for is to talk about what it means to be a scheme over a ring, an A scheme. Or more generally, a scheme over a scheme, so an S scheme. So let S be a scheme. An S scheme, in case this wasn't confusing enough yet, S scheme is... Well, I haven't yet told you what a scheme taking points in a scheme means yet, and that's even crazier. Okay, anyway. This is a scheme X and, well, let's say, is data X with a map to S. And so then the morphisms between these things have got to be some commutative diagrams that respect this. So morphisms Y's got a map to S, and so a morphism is one of these arrows from X to Y that's going to fill in the diagram.
So it's like an S algebra, but for schemes.
Right.
Exactly.
Yep. Yeah, and this is what I'm going to talk about right away here, because you can specialize this when S is spec A of some ring A, and you're basically giving X an A algebra structure when you do this. So if S equals spec A, we say A scheme rather than spec A scheme, because why do we need the spec? Okay, so, but if you remember, if you're really paying attention to what we've talked about, we've already defined what it means to be an A scheme. We, by hand, just said, okay, what the heck is an A scheme? So we have an old definition of A scheme. And Grothendieck would certainly say that our old one is the wrong definition of A scheme, because these should always be phrased in terms of properties of morphisms and not properties of the objects themselves. So that's what we're trying to do here now, is reformulate the old definition in terms of a morphism property instead of a scheme property. The old definition, so we said, and I think Pat was the one who brought this up, so X is an A scheme if, let's say this, sections over any open set is an A algebra for all open sets U, and then the restriction maps must also be A algebra maps. So they have to respect this A algebra structure we've bestowed on all of these rings of sections. Okay, so why is this the same as giving us a morphism from X to spec A? That's what we want to see. And this key proposition, not surprisingly, will be helpful. So let's do the easy direction using this key proposition. So if X is an old A scheme, we know in particular that the global sections of X are an A algebra. So by the fancy definition of A algebra, that's just a homomorphism from A to my ring. Okay, now I apply the proposition to get some map to spec A. Bam. So I didn't actually need the full force of the old A scheme properties. I just needed that the global sections had some map in from A, and I could already give you a map to spec A. Okay, but what about the new A schemes? So one of these A schemes that was just born, shall we say. Well, I want to give A algebra structure to all these sections. So I already know the map to spec A will give me a map from A to the global sections. We get a map from A to here via the proposition. And the most natural thing to do this for any open set is just to keep restricting. Compose this thing with the restriction maps. So if U inside X is open, we take the composition map. There's our A algebra structure. And it's compatible with restrictions because restriction maps commute. So I can just write down this. If I've got some other v inside U, well, we know that the map giving the algebra structure here is this composition. And now I can look at this little arrow, restriction from U to V. And we know that if you restrict and then restrict, it's the same as if you'd just gone all the way there in the first place. So this little triangle commutes. And so the A structure I had here, followed up by restriction, is the same as the A structure I have here, and therefore it's compatible. Okay. So new A schemes and old A schemes are the same A schemes. But from now on, we'll think of them this way. Okay. So I have some time to say something about this proposition. Okay, let's do it. So, as I was just saying earlier, the map going from here to here comes easily. If x to spec A is a map, global sections gives a map from A into here. Okay, now this crazy gluing thing happens. So if I've got one of these maps, given a map like this, we're going to construct an affine open cover of X. Just pick one. Okay, so once we've done this, I can restrict to each of these affine sets, which will be a map from A to BI when I compose through everything. So composing with restriction gives A to global sections to BI. Okay, now I've got a ring map from A to BI. Ergo, by equivalence of categories, a map from spec BI into spec A. From spec BI to spec A. Okay. These spec BIs cover X. So I've now produced a map for every open set and some cover. I would hope to glue them together. Okay, want to glue these. To glue, we have to check this agreement on overlaps business. Okay. UI means spec BI. Okay. And this is my preferred strategy is going to be that thing I mentioned. I'm going to cover this intersection with a bunch of affines and check that the induced global section maps are the same things. So to make the notation just a little nastier, let's cover the intersection. All right, let's let, I will still keep calling them this though. Let's take a union over some set of k's, spec C, I, J, K. Okay, so we check. What we're going to check is that pi I restricted to spec Cij is pi j restricted to spec Cij. Then there's sort of a morphism identity axiom. Just as there's a morphism gluability, you would make the same kind of argument. So I've covered this intersection, and the morphisms agree when restricted to everything in this cover, and therefore they're the same morphism on the bigger thing. Okay, so the reason I've done this is because, as I said, morphisms from affine to affine are easy to check agreement on because they just correspond to ring homomorphisms. So these maps, they run from spec Cijk to spec A. And then the induced map on global sections maps, say, corresponding to these two. They are the following. So anytime I restrict to an open set, we know that the morphisms are just the restriction maps. So these things are massive compositions of a bunch of inclusions followed by this last map we talked about. So on this side, say we've got our map A, we go into here. That was the global section map. We restrict down to here. All right, and then we go all the way down to this spec Cijk. So let's just say this ring is Cijk. That's that one. And the other one is, well, I go different path. I go through uj instead. This is another restriction down to Cijk. And restriction maps don't care about the order. Therefore, it's the same map. So we've got it. So there is a map pi from X to spec A, gluing these together. There's still one more thing to do, which alas, I don't have time for. Or should I say I'm happy I don't have time for, is to check that these two procedures are inverse procedures, that if I started with X to spec A, I took the global section map and then did this gluing thing, I recover the original morphism, and then if I start with any map from A to global sections, do the gluing thing, and then take the induced map on global sections again, I recover this map. So this one must do as a technical thing again. Just fumble through it, as I fumbled through saying that. Okay, thank you. Hope this was clear.